So in that last section, we were finishing this little block on the test hit sheet about ionization energy, and there are several questions in a row that are very closely related to each other, dealing with what ionization energy is and the trends and what causes those trends. And when we broke, we were talking about how ionization energy increases as you go from left to right across a period. The reason for that is because the atoms are getting smaller. So you have small atoms, so you have a very large attraction between the nucleus and those valence electrons. And the nucleus just does not want to let them go. So the ionization energy goes way up as you move over here. We were also saying that ionization energy goes up as you move upwards in a group, because again, the atoms are getting smaller, and those valence electrons that are already there are closer and closer and closer to the nucleus. As you move up and up and up, the atoms are getting smaller.
So even over here on this side of the table where the atoms are getting smaller, because as we go across an energy level, the nucleus is pulling those electrons in. What if we were talking about one, say, in a halogen, an element down here versus one up here? This bigger, what you're saying, I think, is that this bigger atom, even though it's on the smaller left-right side of the chart, this bigger one is going to have a lower ionization energy than this one up here. Did I say that right?
Yes, it's going to be easier to pull this guy's electron off because it's farther away from the nucleus than it is to pull this guy's electron off. And that's within a column. If you compare in a row, it's going to be a lot easier to pull this guy's electron off than it is to pull this guy's. This one, he only has one electron.
Way over there.
Way over here, he only has one electron, and it's way far out.
Yeah.
Way far out. So these trends are very closely related to size of the atoms. Size of the atoms. So which element is going to have the smallest in general? In general, which one's going to have a low ionization energy?
Oh, that would have to be a metal.
Have to be a metal.
And over there in that lower left corner of the periodic table, because they're big and they only have a few valence electrons.
Okay.
All right.
All right.
Now this next question, we're all the way down to test hint number 40. And this is one we know we need to spend some time on.
We got to do 39. 39. What happens if you pull the first one away? But what if you want to take a second one away? What happens to the ionization energy for that second electron? Let's say it costs 10 units of energy to pull one electron away from this one. What if we want to pull a second electron away? How many units of energy in general might that cost? Is it going to cost only 8 or 9? Or is it going to cost 15 or 20? What do you think?
To take another electron away?
A second electron.
Okay, so maybe we've got, let's see, that's 1s2, 2s2, 2p6, 3s1. So this would be sodium. It's kind of a Bohr model diagram of sodium. It's got this one electron way out here. And it's the only electron in that energy level, so we zap it with some energy, or another atom would, and we be able to pull that electron away with whatever its ionization energy is. And we get rid of that. But, okay, so now we've canned this electron. It's gone, but we still have the same number of protons in the nucleus. So now there's more protons than there are electrons. There's one more plus charge compared to the amount of negative charge we have. So that nucleus is going to, does it want to let these other things go? I mean, that's a full outer shell then right there. So that nucleus is going to hold on to these others. We want to pull an electron from this next inner level. We're going to have to add more energy to it.
Right.
And not just the same amount again. it's, you know, probably
Right.
quite a bit more energy.
Right, to make things worse, in this particular scenario, now you're breaking up a full energy level.
Right.
And we spent the whole first part of this testing sheet telling you about stability
Right.
of full energy
And
levels and all that
levels.
stuff. So it's gonna be really tough to bust up this full energy level. It's gonna take even more energy.
And the actual amount of energy is going to be different for each element. And it's, you know, how
Right.
many electrons it has and how many protons are in a nucleus counteracting that. So this is not something where we can say, well, it takes 10 for this and then 20 for that or
Right.
50 for that. It's not that easy. But this data has been determined experimentally and it's published in tables. And, you know, in some of these questions, we're actually going to give you the ionization energy numbers and look for the pattern there. Yeah, when you take away one, that's going to take a certain amount of energy. When you take away the next one, that's going to take more energy. When you take away the next one, that's going to take even more energy. But somewhere along the way, when you're taking away those electrons, there's going to be this huge jump where you're not just increasing by a few hundred or a few thousand, it's going to be like tens of thousands of kilopairs worth of energy, for example's sake. And when there's this really big jump, then you know you've started into this inner shell, this stable octet. So you need to be able to look at the pattern in the numbers and find where that jump is. The cool thing is the periodic table will help guide you anyway.
Right.
You know, even if you're not sure on the numbers, look at where it is on the chart. Look at what kind of ion it would like to form or tend to form. And you can double check that way.
Right.
Okay, are we good? Then with 39 and 40?
We can go to 40. We have time to do 40.
Well, I thought I was
Oh,
just
yeah,
kind of doing
yeah,
that, talking
yeah, you
about
did.
this 40 is going to have
Yeah.
the numbers in it.
Okay, then let's take that break.
All right, let's take a little pause right there.